Good afternoon, good evening, and good morning, depending on your location. This is Wan Kim, organizer of the ABC Forum. I would like to welcome you all to the second annual forum on ABC, or AI and Big Data Convergence. I organized this forum to promote research and development in AI and Big Data convergence areas. I believe it can speed up advances in both AI and big data. I'm grateful to Professor Ismail Khalil and Professor Gabriela Coches for including the forum in the iiWAS and MoMM conferences and taking on the logistics and promotion tasks for the forum. I'm pleased that 6 of the outstanding scholars whose work is within the purview of the ABC have agreed to give presentations in this year's forum. As this forum is conducted online, we will play the pre-recorded video of each presentation. After that, the presenter will be available for a real-time Q&A. Without further ado, let's get started. The first speaker is Professor Veni Raju, Dean of Computing, Engineering, and Mathematical Sciences School in La Trobe University in Melbourne, Australia.
Thank you very much for the opportunity to present today. My name is Veni Raju. I'm a professor in computer science at La Trobe University in Melbourne, Australia. And today the topic of my talk is Big Data IoT in Distributed Smart Manufacturing. We all know about these 3 big V's in big data, and today I'm going to focus on the third V, which is velocity or data speed. So why velocity, and what kind of data actually produces high-speed information? So this high-speed data or high-velocity data mostly comes from devices or sensors. So they are not input by a human being. These are normally sensors data that are broadcasted to the air all the time in real time. And these are normally high-speed data. It's very high in accuracy because it's transferred through the internet, and therefore it needs a lot of pre-processing. So the question here is how to filter the data, how to pre-process the data, and how to store them efficiently. So these are the for example, of census data spreads across manufacturing. We also see census data spread across environment or in smart houses. So for this particular talk, I'm going to focus on big data IoT, particularly in smart manufacturing. And we building a digital twin which allow us to do a real-time maintenance of devices or machines within the manufacturing. The idea of digital twin is the concept that we can have a virtual understanding of physical objects through the data that are sent from multiple layers of sensors that we install within a physical object. And this physical object can be a machine, it can be a car, it can be a house, it can be any type of physical objects. So when we just monitoring physical objects which are located remotely using video, we only can see the image. We cannot see what's actually happening inside that object. The idea of digital twin with multiple sensor IoT that actually broadcast information about humidity, temperature, acceleration of the different parts of the objects will allow us to understand the condition of the physical object that we are monitoring. So we have a very close physical representation within the virtual domain, whether that's in the remote screen monitoring about the situation of this machine, for example. So in the dashboard, we can see where the sensors are located and what is the condition of that particular part. So the example that we're going to use in this talk is based on a real project that we've done here in Melbourne. a manufacturing of chemical products which are not suitable to be placed in a city, so it has to be in a very remote area where there is very low population. And it's very hard to maintain these big machines because sending engineer all the time is also not very effective. And having a regular maintenance is also not effective because the machine may be broken between maintenance. So the idea is to know exactly when a machine is going to break down and send the engineer just at the right time before the machine actually is broken, or when exactly the machine needs to be maintained. So the major challenge is because there are thousands of sensors that have to be installed within all these machines, almost like every spare part of the machine will need to have multiple sensors. So how do we ingest the data? How do we absorb the data into the database? How we store them? And most importantly, how do we pre-process them? Because it's, as I mentioned before, there are a lot of high inaccuracy. This is an example of a machine, a compressor, just one part of a machine that we use as a case study here. Every spare parts will have sensors associated with that, and every machine will have, as I mentioned before, multiple sensors, multiple arrays of sensor. A typical size of data just for one compressor, about 600 megabyte per day of real data streams that are stored, for the sensors installed within that particular machine. So the first thing we have to do is data ingestion. So how do we actually retrieve the data from the physical device using, in our case, we use OPC, which is an open platform communication server, or data collector from physical hardware device, convert them into a text file and store them on the data lake, which is located on the cloud. So we're going to use the data repository that's called Data Lake, and many of you probably have used or have learned Data Lake very well. But just 1 minute, just want to give a bit of overview. It is differentiating from the traditional database and data warehouse. A data lake in the traditional database or the data warehouse that we know is very defined structure. It has a schema, and it is mostly used to store text-based data types, and it's mostly based on relational. Data lake, on the other hand, doesn't have a schema, and therefore we can have a very, very diverse data types, unstructured text, image, IoT stream data, and generally we ingest or directly store raw format data into the data lake. So the next thing is we have to do the pre-processing as part of that ourselves. Because there is a direct data ingestion, the data integrity and quality are not high, and therefore we also need to develop some mechanism. And this can be very unique for each set of data, typical set of data, a different way of data pre-processing. So in short, we store this information into the data lake, and in our case, we are using the MapR database JSON, a NoSQL database, and we use the Apache Hadoop as the distributed platform to basically absorb the data stream that come from the OPC, the open platform communication from the IoT, and store that into our data lake. So the focus of my talk today are the two area of pre-processing. I think this is the main interesting part of this, which are directly related to IoT data, and that is noise removal and missing data imputation, which I'm going to mention. I'm going to explain a little bit later why that is important. So in dealing with research, we often use predefined data or pre-processed data or data that is used for experiment. And those are normally already very well pre-process, and we can use it immediately, and we can immediately apply different machine learning techniques or different AI algorithms because the data is ready. But in reality, when we deal with real data sets that come from devices or sensors, there 80% of our time will be dedicated to clean and pre-process because the data quality is very low, and therefore it is unlikely that we can have a quality outcome out of our analytics or AI processing as a result. So the next pre-processing that we are using here are basically noise detection for pre-processing. So we're looking at the differentiation between a significant anomaly to a noise that is caused by, for example, internet problem or a device fault. So we define the phenomenon of machine conditions, and that if we detect we define outlier as noise, and we remove every outlier because we assume that that is noise, then we have a significant problem of not being able to detect when the machine is going to break. So we need to be able to differentiate between real noise because of internet or because of communication issues and the significant anomaly that is actually caused by a machine condition that requires maintenance. So we identify, particularly for machine, that noise that is caused by device fault or noise that is caused by internet fault are spiky. So they are basically interconnection, back again, interconnection, back again, a very spiky situation, spiky like that. Whereas a significant anomaly that is caused by a machine going to break down is slowly slowly changing. So we don't have a situation where machine is immediately broken. There's always a condition before that, slowing down, or temperature getting hotter and hotter and then broken, or acceleration becomes faster and faster and then broke. So that's there is a gradual anomaly happening. So based on this, we actually develop an algorithm to detect how we actually differentiate between this type of spiky anomaly and the slowly changing type of anomaly. So we divide the windows, divide the data streams into sliding windows, and we actually define what we call neighbor contrast and background contrast. So for every window, we actually identify or measure how dramatically the values inside every window change compared to the previous one, and we call this neighbor contrast. We then compare it with the background contrast, which is the size of the deviation between this neighboring contrast with the deviation, the background normal window. So we identify a threshold based on the normal behavior of that sensor and compare it with this neighboring contrast between the different windows. And the threshold is I mentioned, based on the normal distribution of the behavior of that particular sensor in a normal, in a good condition. And the windows with high score, which means there is a big deviation, or big difference with the normal threshold, that is we define that as a noisy window, and the inside points are noise. Now, there is also a problem with this. In the world of machinery, the behavior of machine changes as it gets older. So what we call the threshold, what we call the normal behavior of that machine, needs to change with time as well. So we need to keep on changing and updating the threshold of the sample data that comes from the same distribution, using the same age machine sensors in condition, a normal condition of machine of the same age. So in other words, we cannot expect a machine that is already 10 years old to behave exactly as a machine that is brand new. The norm threshold changes slightly, so we have to keep updating our background contrast threshold as well. So we actually able to perform noise detection more accurately based on this, and not confusing us with a real noise that come from defaults of that comes from communication, for example, and we then be able to do our analysis further. The screen windows are showing the slow changing, unfortunately, because the graph is actually very big, and this a smaller version of it we cannot see clearly, but the red one are the spike which are outlier and we can remove, and the green one are the ones that we want to study because that indicate a machine real significant anomalies. So the next is about preprocessing for removing big gaps, and we have a situation with IoT where the gaps are so big that it is impossible to use the traditional technique. So in normal technique that we know, we have a technique that is called STL, the seasonal trend loss decomposition, where we basically look at when there is a small gap in between, we look at the seasonal. So we look at certain pattern that repeat at certain season or certain times, and we repeat that pattern, or we look at trend where the trend is upward or downward, and we use that decomposition of the season or pattern base or the trend base to construct the missing gap. Now, if the gap is very, very big, this will become very hard because it becomes very inaccurate to fill a big gap using that technique in one go. So our technique is actually using a modified version of STL, where we call it iterative gap segmentation, and then reconstruction and concatenation. So how does it work? We actually divide the big gap into small segments. We actually do STL by reconstructing that small portion using the seasonal and the trend decomposition. We construct that small gap, and then we start over again to construct the next gap. So instead of filling the gap in one go, we divide them into segments, and we iteratively do reconstructing the small gap, do the seasonal trend decomposition again, reconstruct again, and so both from the front and from the back, and it will then meet in the middle. So we do it segment by segment by segment. So we learn the whole pattern again, we fill in one segment. We learn the whole pattern, fill in one segment, and so forth. So we end up with a much more accurate way of filling the gaps. We use real data here, where we actually compare the previous techniques with the techniques that we have done. We publish a few papers in this topic, and we can demonstrate that we have a much closer, more accurate way of filling the really big gap. So as a result, we have this dashboard which allow us to see now all the condition of the different spare part within the machine that I've shown before. We also do further optimization by creating edge computing, which allow us to then have, rather than immediately send all the raw data to the central remote cloud, we actually have edge local cloud sitting in next to the IoT factory. This will allow us to do the cleaning, pre-processing, and the predictive analytics for that particular set of data within the edge computing, and then we process and we store the model into the remote cloud. This will allow more security as well, because we are not continuously transferring the raw data transfer. We actually deal with it within the edge computing. We have actually submitted, not us, but the company that we work with, submitted this project as in one of the competition in 2018, and we won the best industry application of IoT at that time. So thank you. I welcome any question.
Any question? Well, thank you, Professor Rayu, for a fabulous talk. There are a few questions. In your system, what learning models were used for detecting anomalies? What kind of data set was used to train the model, and what is the accuracy of the model that you experienced?
Yeah, thank you for the question. I'm actually very glad that you asked this question, Professor Won Kim, because I think my presentation may have created a bit of confusion. So I call it pre-processing because what I presented are the 80% of the work, which are the pre-processing. The learning model itself that we use for the anomaly detection and detecting which particular sensor pattern linked to which particular machine anomaly is the next part. So that's basically not what I cover in this. So the pre-processing part is the noise detection as opposed to, so when we have a big data, this IoT sensor data, the raw data has a lot of spike, a lot of spike. And the majority of those spikes are noise, simply because of the communication. And when we started working with this, trying to remove the noise, because we just assume outliers are noise, we realized we get rid of important information, which are actually supposed to be used for the predictive analytics, for identifying whether there is a real anomaly in the machine. So the first tricky part is, how do we distinguish between noise and this anomaly? So we actually use the algorithmic base, of identifying what are the noise, which are the spiky noise, and compared to the kind of significant anomaly, which tend to be gradual. And we actually highlight, for example, in our paper, that this is specific for machine. So if we are talking about IoT, let's say from ECG or from the heart, people who has a heart transplant and they have monitoring in their heart, that's totally different. So spiky data may be very dangerous. It may be an indication of there is something wrong with the heart. But with machine, spiky data indicates noise, because machine don't turn off and on, off and on, off and on like that. So that is why we use that particular phenomenon. And in the algorithm, we actually compare it. So you mentioned about the performance and how accurate it is. So in terms of the noise removal, we actually throw in a real data set where we have proper labeling by the engineers of the company and the historical data of the engine. So there are noise and there are real anomaly. We compare our technique with sort of the state-of-the-art outlier detection using whether that's clustering using k-means or whether that's the local density-based outlier detection, or it's dense distance-based outlier detection. And the problem with all the existing work is mostly based on the fact that it's kind of have a predetermined value of what is an outlier. Whereas in our case, we cannot have a predetermined value of what is outlier and what is not an outlier, because that depends on how the machine behaves as it goes. And with k-means, for example, it requires us to understand the size of the data, but it's data stream. So definitely we cannot decide the k, how many k we should have. So basically a lot of the existing work, when we tested, there are a lot of false negatives or false positives. So it's not as accurate as the technique we use is all very relative to neighboring window. So we actually detect the outlier based on how close the next window is to the previous window, as opposed to an absolute value. So I hope that was a bit long.
Okay, thank you. Just one more question.
Sure.
You have presumed that the breakdown will be with the equipment, but what if the sensors break down? That is, does the breakdown of the sensors manifest itself in the data set? If so, does it manifest simply as noise?
Yeah. So thanks for this. Yeah. So it's really interesting that the breakdown of the sense, basically machine failure depends on a number of sensors. So one sensor only will not cause a breakdown in the machine, because there are many, many sensors and we have a lot of redundancies in the sensors attached to critical part of the machines as well as alongside across the machines. So how to detect machine is going to break? There has to be a multiple series of sensors that are gradually declining. So it can't be, and it has to be interconnected. So we know that if this is getting hotter, this side must be very hot as well. That one must be very hot as well. Then we know it's not a sensor issue. But if there are sensors that are very close to each other and they're a group, only one of them is very hot or suddenly sending very, very dangerous message, we know it's something wrong. It can't be just one sensor detecting heat and the other ones all say cool and no issue. So that's how the to almost guarantee the reliability, I think, of the detection is to make sure that machine fault is not determined just by one sensor. There are multiple interconnected sensors. Yeah.
Okay. Is there any other question from the audience? Well, if not, thank you for your participation, for Professor Ryu.
Thank you. Thank you for having me.
The next speaker is Professor David Tania with the Faculty of Information Technology in Monash University in Melbourne, Australia.
Medical informatics are basically research about health and healthcare that use technology. So that's why AI and big data is an important part. There are many names for this: medical informatics or health informatics. Some people call it digital health or public health informatics, but for simplicity, basically assume that there are research on health and healthcare that use technology. So this research is basically applied is an important part. We use there are many names, existing technologies for this: medical informatics, big data, health informatics, deep learning, digital health, medical health, data engineering. But for simplicity, applied to basically assume that medical informatics, health informatics on health and so it is about how to use the technologies and the research in AI big data and apply it to this area. So this is very different from blue sky research, which is pure research, which basically propose new techniques or methods, right? But in this case, it is different. So in this research, sometimes, especially if my students present, some people may not understand what the contribution is because it is not like proposing new techniques, right? But in this talk, I'm going to highlight opportunities and projects whereby we can actually see the result in those areas. So the first one that I'm going to discuss is the use of electronic medical records. So EMR is basically recording medical records of patients. And from there, we can apply AI and big data techniques to get some result. So this is the first project that I'm going to share it with you. It is about disease progression using sequential pattern mining. So this is a collaboration with Taiwan. So our team had access to this health data set from Taiwan, consisting of more than 2,000 patients and almost 20,000 hospital visits. So after we use data pre-processing, and then we apply sequential pattern mining, which is a well-known data mining techniques to actually find disease progression. So in this case, we focus on myocardial infarction, which is basically heart attack. And based on our analysis of data, that the first year after the heart attack is very important. So we need to analyze what kind of diseases that may progress before they get heart attack. So from this research, we found this disease progression. So as you can see here, diabetes, if you get diabetes, from after a certain year, certain month, then potentially you may get myocardial infarctions. But it is interesting from our research that urinary tract infection. So this is also an important risk factor. Right. So it is a new technique. It is not a new technique, but the result is very interesting and very important, especially for medical profession. The second one that I would like to touch is data warehousing and dashboard. As you know that maybe you've heard from the literatures that electronic medical records are actually seldom used for decision making. I read from the literatures, it said that only 3% of electronic medical records are used by doctors for decision making. So basically, they are only dumping grounds. They only store data, and it is very rare to analyze. So this is an important project for hospital where we actually build a dashboard. In this case, blood transfusions. So in this case, we analyze blood transfusions because when you're having a blood transfusions, you need to be monitored, right? Before the transfusions, and then 15 minutes after the transfusions, 1 hour if your transfusion hasn't finished, and after 1 hour after you finish the transfusions, right? When you look at the data, you might not be surprised that the data is very dirty. Nurses may not follow this particular policy. So in this case, we build a dashboard so that the management can see the compliance rate and then see how to improve the practice in hospital. So the lessons that I learned from this research is that we use AI big data techniques, and we use real data. But unfortunately, it is private data, so we need to get access. We need to get access and work with medical professionals, medical doctors. And there is a small window for research, real research in computer science. So it is not purely applied, but because by understanding the data, we understand new need in terms of new methods in computer science. And you can actually see the real impact immediately in practice. The second one that I would like to touch is using public data, especially for public health. The first one is about COVID, and our work is motivated by this paper, which was published in JAMA, which is the top medical journal, written by a Korean author. So they analyze, in this case, in this paper, they analyze the impact of restricting gathering, and also when they relax the gathering, but they do more testing in the public space, like for example, schools and so on. And you can see actually the increase of the R value and then decrease after that. So this is very interesting. So we did the same thing or similar thing, but in Melbourne, Victoria. So in this case, we analyze the public data about infection rate, lockdowns, because we had lockdowns, severe lockdowns last year and 2 years ago. And then we analyze, this is the R value, which is the infection rate, and also various factors, like for example, lockdown effect in the residential, in public transport, and so on, right? So in this case, we use entirely public data from the government website. The second one that I would like to touch is that the opportunity to use GIS. Now, this is the project that we did with a home birth program in Victoria. So home birth is basically encouraging women, pregnant women, to give birth at home. At the moment, it is probably less than 1%. The government wanted to increase to 2% or more, right? So basically here we analyze the data and then where they live, because there is a condition, then the pregnancy should be normal, and you must have access to the hospital within 30 minutes, right? Just in case if there is any complications, right? So here we plot 32 hospitals in Victoria, and then this is the city of Melbourne. So we plot this, and then we also analyze the distance, 50, I think 5, 10, and 20 kilometers. And then this is the map of Victoria, which is the state, and then this is Melbourne. All of these are actually hospitals, and then we can find out, you know, the catchment, and then how many women potentially can be reached, right? So this is very good for decision making by the government, because here we are talking only public hospitals. At the moment, only 2 public hospitals are funded for home birth, but in this case, we can influence the government to actually fund more, depending on the area, so that more women can participate in this home birth program. The lessons that we learned from this public data and public health is, of course, we use public data, so it is easier compared to the first one, which is private data. And we use biostatistics and machine learning methods to actually analyze and then present to the public, and hopefully it will be useful for decision making. Okay, and we also realized the potential of GIS, analyze the map. The third one that I would like to explain is, of course, medical imaging and explainable AI. So in this case, we analyze data about the brain that has, in this case, the disease is called multiple sclerosis, MS, which is a disease that will make you cripple over the years. The difficulties in this case is that the lesions are very small and there are a lot compared to brain tumor, which is one big one. So identifying this is quite difficult, even for the expert. So here we use deep learning to actually find the lesions, right? The most important in this work is basically explainable AI. Right? So basically, we would like to explain how we come up with this segmentation. So XAI is basically the next thing in medical imaging. So if you are interested, the lessons that I've learned is that it needs big CPUs because it is very time consuming. If you use your own laptop, probably processing like this will take 5-6 hours. My student initially used Google Colab. We could reduce to maybe about 4 hours. But luckily, Monash has a big cloud system, supercomputer, and we could reduce the processing time to 1 or 2 hours the most. And also, we use public data. There is potential that we can use private data if we work with medical doctors. Right? So it is a very hands-on practice because there's a lot of competitions in this area that your team might want to participate. The fourth one is the questions of how to use computing technologies, in this case, IoT and cloud. Right? So I'm going to explain to you this project, which is basically using cloud technology to detect early kidney disease. So if normally if you want to detect early kidney disease is that when you have a blood test, like yearly blood test, you actually want to see this albumin, right, which is a protein in the blood, right? That level may actually identify whether you are prone to kidney disease or not, right? But of course, kidney disease is often found, in certain population, and we would like to detect kidney disease earlier. Right? People normally use urine, so they test the urine, okay, to check the level of albumin. But again, you have to go to the lab and then you test the urine. So the idea is that if we use infrared, okay, so we can get infrared and then shoot it to the urine, okay, and then do classification, machine learning, and then to identify the level of albumin, right? So this one is that we use cloud technology, and then after that we can monitor it in mobile, or in case of doctor, you can do data analysis. Right? Now this is very interesting. We are starting to use this infrared, near infrared technologies. Collaborate with the expert in the School of Chemistry, and then our team from the computer science. We are just dealing with the cloud technology, as well as the machine learning to do the classifications. Right? So this is an important progress. The second one that I would like to explain is the opportunity in the hospital. When the doctor and nurses want to see the patient, as you can see here on the right-hand side, right, there is a alcohol dispenser. So they have to wash their hands before they handle the patient. And after they finish handling the patient, they have to wash again. But sometimes it is very difficult to monitor, right? Yearly, the hospital use audit system, and they just place someone to see. But what we want is that we want to do automatically using sensors. So we place sensors attached to the alcohol dispenser so that they can see whether the hand washing is actually done or not, right? So there's a lot of IoT technologies used, a lot of data processing, because when you have multiple beds in one room, right, and then we have a few detections, so we want to make sure that the detection is correct for that particular patients. The last one that I would like to touch is that monitoring using mobile phone for chemotherapy side effects. So this is a collaboration with hospital. Normally, when you have a chemotherapy treatment, right, every 2 weeks, say, for example, you might experience side effects, right? And when you go to the next chemotherapy treatment, the doctor normally asks you what is the side effect that you've already experienced. But sometimes the patient forgot, right, during the 2 weeks. So what we want to do here is that we build a mobile app, okay, so that they can report the side effect real time when they experience it. And there's a different level of side effects. And then the nurse can actually monitor. And then if they need to send it to hospital, they can do it immediately. So the lesson is that this work is very important. The impact is real. Health monitoring is very important. So a lot of opportunities in this area. The last one before I finish is brain informatics. So this is new. We analyze brain signals, okay, for various reasons. So in this talk, basically I highlight a few opportunities in medical informatics research, especially using AI and big data technologies. Right? I believe that there's a lot of opportunities. So if I invite to collaborate, let's work together so that we can achieve more results. Yeah, I can bring in my team, and then you can bring in your team, and then we can work together in this area, which is an important area. So thank you very much.
Is there any question on this talk?
Hello. May I ask a question?
Professor Eun-Ki Lo of Gachon University. Please go ahead.
Yeah. Professor Tanya, thank you for your comprehensive presentation. I would like to ask a question about data security. There are many people and organizations that are not willing to share their sensitive data, especially for medical applications. I am wondering if you have any ideas or methods to cope with the problem.
Thank you for the question, Professor Lo. Nice to meet you again. There are two things. One is data security and the other one is privacy. When we are working with medical professionals, we are actually solving their problems. So the projects that were described, I mean, they are not from our side, but it is because of their needs that they want to have this, and then we come in to actually help them. So in that case, the privacy issue, they handle it. So we don't have access to the like, for example, patient name and so on, right? Because they already de-identified. The second is the security. This is an important issue. When we got the data, first of all, they would not want us to bring the data outside their network because it is, they just don't like, outside people to bring the data, right? because some of our partners are from our hospitals, so within the same network. So it is still okay to move the data around Monash network because it is the same network. But there is one thing that is important, and some people don't know about this, is that when we use, for example, tools for dashboard that is cloud-based, like for example Power BI or something, when we actually plot it, the data is actually copied to that environment, and that environment is actually a cloud environment. So after checking for a while, then we noticed that actually we don't have any control where the data is located because it is already in that, for example, Power BI Microsoft environment, right? So now because of that experience, we learned that from that experience that now we use more traditional, like for example, we can use Python to build, or we use Tableau just to make sure that we don't use the cloud system to access the data because we store the data locally in our environment. So yes, if it is within the same network, then that should be a problem. Just make sure that we don't use any cloud technology. But if it is different hospital, like I'm working with another hospital, then we need to go there. They need to create us an account to get access to. We cannot bring the data out. Mm-hmm. But I think the most important is that they realize that it is the problem that we can solve, and they're willing to work with us, with computer science, because we bring that expertise, and then we can see the result. They can see the result immediately that that helped them. I think that is the most important for us.
Okay, thank you for your answer.
Thank you.
Any other question? If there's no other question, Professor Tanya, I'd like to thank you very much for a well-prepared talk, touching on a wide range of important subjects. And I know that it's approaching midnight in Melbourne, and you have a long day tomorrow. But if you would bear with me, I'd like to ask one question. Today, with or without AI, only trained medical professionals can understand medical images, such as CT, MRI, and X-ray images. And I'm curious, just how much explaining do you think explainable AI should provide with the results of deep learning applied to medical imaging?
Well, thank you very much for question. I think the issue of explainable AI is important nowadays, but I need to highlight two things. One is that we do not expect that AI will ever replace medical doctors. So whatever decision that we come up with, it is only to help medical professions. And the second is that AI, in this case deep learning for medical images, works as good as the data that we get. So it is basically based on the ability of computers to remember other similar cases. Yeah? So if you are a senior radiologist who actually see medical images every day, every time you see a new case, it is not a new case for them because maybe they have seen it many times in the past. Right? But for junior radiologists that haven't seen so many images, right? Maybe there are some images that they are not sure, right? Especially in the third world country where the ratio between patient and doctor is high, and not every hospital has, for example, qualified radiologists. So this work will help them to see that there might be potential issues in the images, right? There might be potential lesion that they may not see. Then they can bring up, to their seniors to discuss. So that is the aim of medical imaging analysis. Now, in terms of what kind of explanations, this topic, this work is still new. At the moment, we only, because when deep learning produces the result, it doesn't tell why the result is like that, right? It only tells you that this is the result that the model gets, right? So at the moment, what people do is that, also us, that we try to explain how that decision is made, okay, through intermediate steps. And it is actually pixel-based. So that is one thing to explain that this is the result, and then these are the intermediate result that produce that final decision. Another one is that we use Heatmap, saliency map. A lot of people use that, and a lot of function libraries in Python, in Keras, PyTorch as well, to actually show. But it doesn't actually explain beyond what medical doctors need to know, right? What is ideal is that the explanation should explain from any outside data. Say, for example, if the tumor is inside the, for example, liquid, for example, when you see it, even radiologists cannot be certain because you cannot see, right? Is there a tumor behind it or not, right? So even radiologists may not fully understand that, right? But with AI, hopefully we can bring in, from past experience, from past images, that we can say that perhaps 75% inside that area is a tumor, right? So that is one thing. Another thing is that even with an expert, they may not agree each other, right? Because of various cases. For example, we are starting to work with the dentist in the X-ray to identify problems in the gum. Sometimes they also cannot see because it is behind something. So hopefully with this AI big data, we can highlight something. With certain confidence, we can say, okay, this could be the problem, and hopefully that will help doctors and radiologists to take up this technology as an aid for them. Yeah. I think this area is growing. I invite everybody in this call to, if you are interested, to jump into this explainable AI, especially in medical images, like what you are doing, and a lot of opportunities. And I know that some of you experience, the loved one, experience this kind of disease, and we want to find the answer. That's our contribution.
Okay. Thank you again for your participation, Professor Tanya.
I have a question, Professor Kim, if you don't mind.
You have a question?
Yes.
Oh, go ahead.
Thank you, David, for the excellent talk. And one of the concerns of researchers working on medical informatics is privacy. And
sorry?
You mentioned privacy.
Yeah.
Okay. So how are you going to differentiate between public data and private data? Are you going to, for example, train the model on the public data first, then train another model on the private data? Or how can you find this balance so you don't violate the privacy of the users using the system?
Yeah, thanks very much. For the public data, what I mean is, like, for example, analyze, reproduction in COVID, say, for example. Then we use government data, various places. One is the COVID number every day. The other one is probably lockdown policy and so on, right? So it is more on how to actually do the data linkage and then combine the data so that we can analyze further. So there's no actually privacy problem. So whereas the private data is the hospital data, so we never combine the public data and the private data. So for the hospital, they already protect that privacy, that we don't have access.
Thank you very much. Thank you.
Okay, I guess it's past midnight in Melbourne, so I hope that you have a good night's sleep, and then sometime soon, come visit Korea again.
Thank you.
Let's enjoy some street food in Myeongdong together. Thank you so much.
Thank you so much.
The next speaker is a wonderful colleague of mine, Professor Ong-Lan Jung, with the School of Computing in Gachon University in Korea. Paul?
Hello everyone, welcome to this presentation. I am Ong-Lan Jung from Gachon University in Korea. It's a pleasure to present at the ABC Forum. Today here, I talk about AI frameworks for intelligence data analysis. In particular, I'll discuss the techniques that utilize the knowledge graph and the conversation AI framework based on it. One of the many key technologies that make AI faster is how computers understand the common sense of humans. In this presentation, I'll introduce the Beijing research background, machine learning with graph and knowledge graph. And I will talk about in detail the conversation AI framework based on auto-growing knowledge graph, designed and implemented by our research team. This is a brief introduction to the research background. Intelligent data analysis is one of the hot issues in the field of AI. As you know, first of all, what's the definition of information and knowledge? Information is generated when data is processed, organized, or structured to provide context and meaning. Knowledge is what we know. Knowledge is unique to each person, and past experience and insight are accumulated to form perspectives that interpret and give meaning to information. Intelligence data analysis is the transformation from data to knowledge, and it uses statistical pattern recognition, machine learning, data abstract, and visualization tool for data analysis. As such, it reveals implicit, previously unknown, and potentially valuable information or knowledge from large amount of data. A graph-based data model that describes neurons, entities, and relations between them. The knowledge graph collects information, integrates it into an ontology, and applies reasoning to derive new knowledge. Let's take a brief look at the graph of knowledge of the Mona Lisa. Blue circles are entities, and links between them are relationships. The Mona Lisa was painted by Leonardo da Vinci and is in the Louvre, and the museum is located in Paris. Chatbot is a type of conversational AI. As you know, chatbots are software that conducts conversational via auditory or textual method. It's the easiest access system for convergence technology using AI techniques. Research is being carried out to enhance the performance of chatbot by applying a technology to NLP recognition and creation in order to communicate with humans based on graphs. Data are represented in graph form for information. Graphs are general language for describing complex systems of interacting entities. Many types of network data are represented graphically, such as social network, economic networks, communication network, information network, internet network, and neurons, and so on. Graphs are general-purpose language for describing complex data. It's also shared vocabulary between fields. It applies to solving data availability and computation problems. In addition, discover many facts and relationships in social network, drug design, agile reasoning, and more. Graphs are used for knowledge discovery. Behind many systems, that is an intricate wiring diagram or graph that defines interaction between the components. We'll never be able to model and predict these systems unless we understand the graph behind them. Graphs are used for node classification, link prediction, community detection, network similarity, and more. Based on analysis methods of these graphs, let's look at knowledge graph application technique. Let's take a look at the knowledge graph. Knowledge in graph form captures entities, types, and relationships. Nodes are entities. Nodes are marked with their type. And edge between two nodes captures the relationship between entities. Knowledge graphs and knowledge base are used similarly, but let's compare them. A knowledge graph acquires and integrates information into an ontology. It applies a reasoner to derive new knowledge. It contains knowledge derived from the knowledge base. Knowledge graphs has been used in many projects. For example, OpenCYC, Wikidata, DBpeer, Yahoo, NER, Google Knowledge Graph, ConceptNet, and so on. Knowledge base contains all the information that is collected, such as an ontology. And stored information is a sub-concept of knowledge graph. Therefore, knowledge graphs are superior concept of the knowledge base. In other words, the biggest difference between knowledge graph and base is a difference between knowledge and information. An example of knowledge graph is ConceptNet. ConceptNet is open multilingual knowledge graph. It originated from the crowdsourcing project OpenMind Common Sense, which was launched in 1999 at the MIT Media Lab. It covers 10 core languages and 68 common languages. However, as is shown in this table, it is focused on core languages. ConceptNet has 34 relationships. For example, if a relationship is car is vehicle, and the hazard relationship is bird has wings. ConceptNet is using it as important base data in recent research trend because it represents the general relationships of words used by people in knowledge graph. Next, I will introduce conversational AI framework based on auto-growing knowledge graph. There are many solutions for big data processing and management. There are MongoDB, Hadoop, Hive, HBase, etc. Then you use and know a lot. In this project, Apache AstroDB is used. It was developed by UC Irvine, UC Riverside, UC San Diego, and Couchbase. And our team has been participating in the research since 2015. It built a new big data management system and conduct scalable information system research. One-size-fits-all can offer better functionality, manageability, and performance than gluing together multiple point solutions. For example, Hadoop plus Hive plus MongoDB. It has advantages such as flexible data model, efficient runtime, full query capabilities, and designs for continuous data ingestion. It can support today's big data types. Polaris project is part of Apache AstroDB project. Polaris is a brightest star in the north of compass. It's an interactive system to provide, analyze, and predict results, such as event detection, trajectory, sentiment, and semantic analysis. Polaris X is a Polaris expander, an auto-growing knowledge graph to expand Polaris. Polaris Export is a Polaris X-based intelligence chatbot using auto-growing knowledge graph. From now on, I will going to talk about these three Polaris projects. Polaris is a big data analysis and prediction system. It has the following characteristics: real-time big data crawling using AstroDB, machine learning-based analysis system, deep learning-based prediction system, and visualization on the result of analysis and prediction. In Polaris system, we use tweet data to analyze the positive and negative of a particular event. This figure shows the positive and negative analysis by time and reason when it snows. This analysis allows us to predict the emotions of a particular reason at the following time. The main features of a Polaris system are efficiency on cost, sentiment path, and deep learning on sentiment path. For sentiment analysis, we use machine learning to analyze the sentiment users for the event occurred. The sentiment classification model is trained using the CNN for sentence classification. For sentiment path prediction, the concept of time window is used based on LSTM. This is an overall structure diagram of a Polaris system, crawling data, analyze, visualizing results, and predicting them. Examples of analysis result for snows. When it snows, it snows the trajectory of tweets about snow, and analysis of positive and negative. Blue circle indicate positive, red circle indicate negative. Next, I'll talk about Polaris X. Polaris X expands the knowledge graph automatically, not only to rapidly expand the knowledge base for any human language, but also to support the algorithms. It collects big data in real time, extracts new Earth and their relationships using deep learning, and find out the meaning of new words. Existing knowledge graphs have the following limitations. First, the existing knowledge base is rather limited in size and scope for most of human languages. Second, it's not able to support in timely manner the algorithms that form a part of human common sense. Polaris X consists of social clusters, semantic analytics, and knowledge minor component. Let's look at example of the algorithms. We couldn't find the word therapy in the existing knowledge graph because it didn't exist before. The Polaris X-based system shows the following result in relation to easier and related to. Therapy is self-portrait and related to travel. Here is an example of language dependence free. The sonata is used as a Hyundai car in Korea. However, foreign countries recognize the sonata as classical music. Recognize that sonata is commonly used as a car in Korea. It shows the result of sonata is a car and has a tire. This is a structure diagram for semantic analysis of the algorithms. Polaris X has semantic analysis using the fine-tuned bot model. The figure shows the sonata is extended to the car graph through semantic analysis of Polaris X. This is the architecture of Polaris X. It consists of social crawler, semantic analysis, and knowledge miner. In the first step, data such as social media, news, etc. are collected. Semantic analysis is performed in the next step. Knowledge is extracted in the last step, and the graph is expanded. This is a conversational AI framework based on auto-growing knowledge graph. The red dot box below is a Polaris X part and consists of a machine learning layer and presentation layer on it. A conversational AI framework can be constructed with this architecture. Next, I'll talk about the Polaris X book. It's an intelligence chatbot using an auto-growing knowledge graph. It applies knowledge graphs that can help us understand human common sense to chatbot that talk with humans so that we can learn general knowledge, common sense from computers. Polaris X-bot finds answers to questions based on previously described knowledge graph and displays the result. This is its structure for extraction new relations and expanding knowledge graph. This is a simple example of a Polaris X-bot. When user asks a question about a car, the user and has relationship answers. A car is a motor vehicle and a car has a seat. In addition, it shows a relationship graph. Now, let me give you a conclusion and I will wrap it up. So far, I've talked about the Polaris project. Our project is based on conversational AI framework. Specifically, this framework was designed and implemented based on Polaris X. Finally, the purpose of this research is to understand the common sense of human beings to computers, to enable more multi-aspect analysis and prediction of big data, and to build AI frameworks based on Polaris X. Thank you for listening.
Any questions from the audience?
May I ask a question?
Yeah.
Please go ahead.
Yeah. Thank you for your concise and effective presentation. I would like to ask about Polaris project. As part of the project, you explained sentiment analysis and prediction. My question is about the relationship between those two subsystems. How are sentiment analysis results used for sentiment prediction?
Thank you very much for your comment and good questions. The result of analysis through our trade model can be utilized for prediction. How users' sentiment process for event extracted in real time will be analyzed. And the result of analysis will be utilized as a model for prediction of the next sentiment. By analyzing the sentiment past, the place where a certain event is expected to occur and sentiment predicts and show in advance. In other words, we figure out the result of sentiment analysis by time units. In this research, the window size of time unit was set to 7 days. By applying the analysis result for each time unit to the LSTM, as you know, long short-term memory, is it possible to predict the positive and negative analysis for the future time. Additionally, it was published in the journal Expert Systemic Application.
Yeah, thank you for your precise answer.
Any other questions from the floor?
Ask the question.
Yeah, please go ahead.
Yeah. You see a relationship. This knowledge graph can only represent binary relationship. How about n-ary relationship? How to represent? That's one more question, like ternary relationship. The other thing is the relationship usually has attributes, like a part supply by a supplier with a price, something like that, right? So there's an attribute of the relationship. Knowledge graph, I cannot see how to represent that. Another question is, when you talk about relationship, the composition relationship never mentioned. Like if you're a mother, father, then you can define something called grandfather, grandmother, okay, or grandparent or parent, etc. Sibling, brother, sister, all this can be defined. These are some sort of rule which define the new relationship from the old relationship for the existing relationship. Like just I mentioned, I say again, you have the basic one, mother relationship, father relationship. You can define parent relationship. You can define grandfather, grandmother, sibling, brother, sister, maybe sister, etc. All this sort of thing. Looks like nobody mentioned about this. Because when you traverse from nodes to nodes, in fact, it's the composition of the relationship. Right? Are they people talk about this? Because all these are, in fact, in the database. Okay, long time ago, people have mentioned about that. Deductive database, all these are there for a long, long time. Okay. So basically, these are my questions.
Thank you very much for your question. Our relationship of knowledge graph is based on concept map relationships. Concept name relations have 34 relationships. Is for example, user has and related to and so on. So we use the basic relationships of concept name.
No, what I mean, okay, those are binary relationship between two objects. But what I mean, okay, you may have the relationship which define among maybe 3 or 4 different type object, or even different object from different classes. That means there is a ternary relationship. All these knowledge graph I have seen are all binary relationship.
Oh, yes, I think.
I mean, of course, I can represent the ternary relationship by binary relationship by creating some sort of nodes which is called the relationship node. But the whole thing becomes very messy, the hypergraph. I can use a hypergraph to define the n-ary, but in the case, that means very, very messy, okay? And also, just now I mentioned about traversal of the nodes from nodes to nodes, okay? Actually, it's a composition of the relationship. When you composition relationship, you must know what is the meaning of the father. Father, A is a father of B and B is a father of C. So in this case, become A is a grandfather of C. That means that's our relationship. So that is the what I say called those are in the knowledge base, last time knowledge base, didactic database, all those things are there. But looks like nobody talk about this one when you talk about knowledge graph.
If I may interject in this, Professor Tok Kwang Ling, it's wonderful to see you. I didn't expect to see you in this forum, but it's wonderful to see you. How's your family?
Okay. Sorry. Yeah, it's okay, quite okay, because I just look at the, I read that one, okay.
What Professor Chung is using is the WordNet, which is limited to about
30, that means
32
I know
types
that that's a binary one.
So that's the starting point. And, So your points are well taken, but Professor Chung's work is based on knowledge graph, which is represented by WordNet, and it supports limited set of relationships.
The other thing is, okay, when you may have the conflict information inside the knowledge graph, may have the conflict one, because when you know, the other one may be a bit difficult, because that means that when it's not like anyhow you can just define the relationship between two objects, okay. It may go for a loop and then go somewhere else, come back, okay. Then in fact there's a conflict if you do not detect properly.
Thank you, Professor Tok Kwang Ling, for the question. I have one question, Professor Chung. When you add a new meaning to an existing neologism, such as sonata in a knowledge graph, is it instantly visible to the user, or does it take some additional work or time for the new meaning to propagate and become visible?
Thank you very much for good questions. When a new meaning is added, the new meaning first goes through the knowledge minor step in order for it to become visible. At this stage, the knowledge minor uses string matching to link newly discovered relationships to existing knowledge graphs. There are two ways to expand the knowledge graphs. One of by connecting the matching node and the new semantic graph in presence of matching node. Another is by just adding a new node in the absence of a matching node. This means the additional minor runs are required.
Okay, thanks so much for the answer. If there's no other question from Professor Wang, Top Guangling.
I have many questions, but it's okay. Especially
Okay.
knowledge graph. Okay.
Well, I'd like to thank you for your participation, Professor Zhang. The next speaker is also one of my colleagues, Professor Jong-hyun An, with the School of Computing in Gachon University, Korea. Paul, let's get started.
Hello, everyone. Today, I represent convergence of AI and big data, the concept of new building trend for autonomous driving, named as crowdsourced mapping. The concept of crowdsourced mappings has not yet been released to the public, and some companies are researching their technology individually. Therefore, today's presentation will brief concept and explanations. In this presentation, I will give a brief explanation of existing map creation method and limitation along with the sensor required for the map. And to overcome the limitations, let's look at the concept of crowdsourced mappings, which I will explain today. And we also learn about the representative technology required for creations. First one is about the sensor for autonomous driving. The most popular sensor is image sensor. As much research is already been done, image sensors are the most easily accessible basic sensor for autonomous driving. Mass production is possible, so the price is low, and a lot of information can be easily measured. In addition to the basic RGB sensor, we can get various information depending on how it works, such as infrared sensor, noise reduction shutter camera. However, the image sensor is vulnerable to change in the brightness of light and is difficult to obtain distance information. To compensate for this shortcoming, a range sensor is additionally used. Unlike the image sensor, a range sensor uses X, Y, and Z as an input measurement, so it can recognize accurate spatial information with the object. The below video shows the measurements of 3D laser scanners. Unlike the image sensor, it is characterized by being able to see in all directions as well as in the front. The last sensor is INS. An initial navigation system is a device that uses motion sensor, rotation sensors, such as accelerometer, gyroscope, and it calculates by data recording the position, the orientation, and the velocity of moving objects without the need for external references, such as GPS. So INS are openly used on mobile robots and on vehicles such as ships, aircraft, submarine, guided missile. So by using this sensor, let's look at how maps were created in the past way. First of all, let's look at the concept of HD map used in autonomous driving. An HD map is a map specially designed for autonomous driving and is generally referred to as a high precision map or HD map. The high precision map includes not only lane level information such as road center line and boundary line, but also information such as traffic light, signal, curve, road marks, and barrier structure of 3D digital formats. In order to digitalize even information that humans can naturally acquire, maps are produced on the scale close to 1:1, because only then can the level of error in autonomous driving be reduced to the less than 10 centimeters. So, to build such a HD map, a vehicle called Mobile Mapping System was used. The mobile mapping system integrates a vision system, radar scanner, GPS receive, inertial navigation systems into a mobile body to build a high-quality spatial information database. The mobile mapping system, MMS, which is considered the most suitable method for acquire various and complex geometric features information in the real world, especially the city, is an integrated system using the various sensors. Since the MMS is composed of various types of sensors, the performance of this system is determined according to the performance of each sensor. However, since these systems are equipped with expensive sensors, it is too expensive to build one MMS system. If all sensors are equipped in a one MMS, the price of one unit is at least several billions. And it is also difficult to create a large city map at once. It is necessary to visit a complex city centers consisting of many nodes. That's why updating map on a regular basis is also costly. For the same reason, when a problem occurs in the HD map, in order to correct only that point, it must be manually corrected by using expensive MMS systems. So, to overcome these disadvantages, the crowdsourced mapping system is invented. The dictionary definition of crowdsourcing is as follows. Crowdsourcing involves a large group of disparate participants contributing or producing goods or services, including ideas, both microtasks and finance. So, if we compare it to the mapping system, the crowdsourced mapping is the idea of creating a large-scale map using not only vehicle and the robot dedicated for map creations, but also those for the regular users. So the user's vehicle make the map. At the same time, it can collect the sensor data and upload it to the central server such as cloud. Therefore, the crowdsourcing mapping consists of three parts. The first one is data collections, and the second one is aggregations, and the last one is localizations. In the first step, each vehicle must collect data. As a single vehicle drives on the road, it collects road information individually. And the collected information is uploaded to the cloud. At this time, the information collected from each vehicle is combined to create one large HTML. This is called SLAM. When the one large map is formed in this way, the other vehicle drive on that map downloaded from the server. When this cycle is repeated again and again, one large map is created automatically and updated manually. Then let's find out what technology are required in each step for crowdsourced mapping. First, let's look at how data is collected. The first way to collect data is using binocular cameras. In the best way, it needs two steps. The first step is region proposal. The region proposal network picks up the region where objects are likely to be located in the images, such as ROI, region of interest. And then the selected ROIs are classified into class by classification networks, and bounding box is bounded. These two-step algorithm provide high accuracy, but has the disadvantage of being very slow. To overcome these disadvantages, it is a new method, new networks has become. Name is YOLO, which is so famous today. YOLO simultaneously locates the bounding box and classify as the final output of the networks. It is quite fast because only one network extracts feature create bounding box and classify them at once. Therefore, using these single-step detection networks, many objects on the road are recognized. In addition to the object detections, it is also distinguished the object at the pixel level. The semantic segmentation is a problem of classifying objects in the pixel unit as shown in the image on the right. To this end, in the encoding step, the dimension is reduced while increasing the number of channels to capture the characteristic of input images. And in the decoding step, a high dimensional information is restored by reducing the number of channels and increasing the dimension using only low dimensional encoded informations. UNet extract images feature not only low dimensional but also high dimensional informations, enabling accurate positionings. To this end, it is a structure in which features obtained from each layer in the encoding step are combined with each layer to the decoding steps. Through this, it recognizes information such as rain and road area that are difficult to distinguish from the former box in the images. In addition, a range sensor may be used as well as image sensor. However, the range sensor provides the data in the form of fluid point cloud such as XYZ rather than RGB. Since point cloud and meshes are allowed in regular format, most methods typically transform the data into regular 3D voxel grid or a collection of images before feeding them to the deep structures. However, these transformations render the result data unnecessary voluminous and also introduce quantization artifacts that can obscure the natural invariance of data. So, the point net directly consumes the point cloud with respect to permutation invariance in the input by using T-net structures. Therefore, as shown in the image on the right, the 3D point cloud can be recognized on the point level as well. When all the information on the load is collected by these various types of sensors, the information must be processed in the cloud to create a final HD map. This is called aggregations. The most basic algorithm to do this is SLAM. SLAM is the abbreviation of simultaneous localization and mapping, and it is a method in which a robot explores an area and makes a map. At the same time, recognize its location on created maps. To do this, SLAM is largely divided into two stages. The first stage is front end, which do key point extractions, information that can be characterized of the currently received data and association between the created maps. The backend performs nonlinear least scale optimization tasks such as bundle adjustment and optimize the global locations and surrounding environment structures. The most used map structure to do this is graph. A graph is composed of nodes, edges, and landmarks. A node means the location information of the robot in the graph. An edge, which is a relation between the node connecting location information and next locations. Landmark create the constraints of such a positioning information between two nodes. These landmarks are the road information collected by individual vehicles which are done from the above process data collections. The resulting graph is optimized in the backend. The vehicle can renew the location information when it passes the place it has been passed, and optimization occurs at this time. Therefore, as shown in the videos, you can check the part where the map check once. At this moment, when the map optimized by graph technology. In the front end of SLAM, which perform key point extractions and key point matchings, the features were extracted manually from the images. So until now, the most used features were indirect features such as shift, surf, brief, and ORB. However, with the development of deep learning, features that can be most relevant are extracted through the networks. The most famous networks among them is Superpoint, which extract the location of 2D key points in the images and the description information of the corresponding features. To this end, Superpoint uses sham training techniques to efficiently learn image pair with good keywords matching with the ground truth data in the running process. Through this, as shown in the figure on the right, it connects the related feature in two different images very well. The process of calculating the positions of optimized load using the information on constraint and load created through the front end is performed in the back end of GraphSlam. Xi and Xj are the position of two nodes in the current graph. At this time, Zij is the position of Xj measured using sensor at the point of Xi. The difference between the positions of nodes measured by the sensor and the position on the current graph is expressed as error Eij. At this time, graph optimization is the process of minimizing this error. Therefore, to solve this problem, Jacobian matrix of error is required, and the many solvers have been developed to minimize it. These solvers are used to solve optimization problems as shown in the right figures. Therefore, through the structure of such a GraphSlam, the feature information collected by each vehicle is used as a landmark, and the data processing is complete by using the locations of different vehicles as a node. Then, as shown in the image on the right, complex data provided by multiple vehicles can be converged into meaningful single data. This can be set to the final map of crowdsourced mapping. The final step is localization. The localization is not much different from the SLAM. However, the states of the vehicle can be expressed probabilistically, and the relative positions on the map can be accurately identified through the filter theory in the form of updating and correcting by using Kalman filters. Then, as shown in the images on the right, the location of the vehicle can be measured with the precise of length on the generated HD maps. Through this, not only one vehicle, which is MMS system, but also user vehicle travel in the various area of the city, and all data is correct and processed at once, it will be easy to maintain and updating the wide and complex city map by using the concept of crowdsourced mappings. And this is my end of presentations. Thank you for listening.
Any questions from the audience? If not, thank you, Professor An, for a very good talk on a subject of great interest.
Maybe I ask a question.
Oh, please go ahead.
Okay. It's here, usually, okay, even in driving, you need to have some sort of knowledge, right? Whether you are driving on the left side or right side, right? These are some sort of knowledge, or traffic light, etc. Okay. So these are what I call the knowledge. So do you have the knowledge of this? Because the driving in US and driving in Singapore are very different, because the left-hand drive, and then the right-hand drive. And maybe, of course, there are some signs also different. Whether actually all this driving, you train a vehicle in US, can you just bring to Singapore and then use that? So second question is, whether this auto driving actually go and learn the other vehicle driving behavior, whether they are very fast, they are very rude, or it's very slow or not. Because to avoid have collision, okay, we must know other user the way they drive, whether the way they drive is regular or very ruthless, okay. So it's been called accident. That is the two questions. One is the knowledge base. Store the knowledge of the rule of the driving. Second one is whether actually they try to learn other vehicles driving behavior or not.
Oh yeah, oh, that's it.
Yeah.
Oh yeah. First of all, thank you for your great questions. On that questions, I just only make a simple reply on that. As the first question and the second question, when they make Heatmap, there are no problem of depend on the driveness behavior or the noisy, because on the only information need for the map creation is the feature, like as road rain and road line, or traffic light. So if they travel the different ways, or they travel very rude, or they drive, they're very slow, there is no other problems to make the Heatmap. So as I answering your two of questions, it simply make I answer that. That is not difficult, not big things to make Heatmap. Yeah, that's it.
Like for example, the rule, okay, driving on left or the right, when you make a turn, okay, 90-degree turn, you go to the different lane. So, sometimes, okay, people who are not, stay in that country, like from the left-hand side to the right-hand side driving, okay, they always make a mistake. That means they're not very careful when they make a turn, okay, turn 90 degree, turn to the other side of the lane and cause an accident. So these are the rule, okay, the basic driving rule are different in US and Singapore.
Okay.
So basically, yeah, those are rules. That means what I mean, okay, you must have a knowledge base, store all these rules. And you don't need to train them. In fact, there's no need to train. This is a sign which is a stop sign. This is a sign which is a slow sign, etc. Okay. To have a knowledge base and use this knowledge base to guide the automobile moving. Yeah, basically that is what I mean.
Okay, right. Let me guess. The knowledge-based rule is can be applied in the field of probability field. We make the motion model. So the vehicle should travel at that motion model, depend on that motion model. So that motion model can be considered as a knowledge. So in the Korea, we go the right side, and the United States, they go left side. So these all the rules make the vehicle model. So as I understand that noisy can be applied in the field of probabilistic robotics, it may be called as motion models.
Okay.
Yeah, that's it.
Okay.
Yeah, thank you for your great questions.
My question is this. Professor Han, you described many problems being solved in the context of crowdsourced mapping.
Yeah.
But it appears that there are some other rather thorny problems. For example, in data collection and aggregation, I expect that there will be lots of duplicated data and even conflicting data. Also in remote areas where not many people travel, you may not have enough data. So it seems that these are some of the problems to look into, and there may be some other problems. So I was curious about your opinion on this matter.
Oh, okay. Yeah, thank you for your great questions. First of all, currently the most popular method to solve that kind of problem called in probability is data associations. So in the field of probability, this approach to the data association has several steps. First, each data has a unique characteristics of load objects such as name, sign, R's, extract. And these unique characteristics called a feature. Then this feature set is made every time when new data is coming. Then when a new load information is received at the step of SLAM sequence, the set of these features are compared with the new incoming features. So if these two features has a similarity characteristic, that the feature can acquire more probability as a good feature. So if these steps are repeated again and again, the good feature has a higher probability value. So the unnecessary or the duplicate data can be filtered out. So I can say that the probability approaches maybe solve the kind of problems. And also, where the vehicle doesn't travel any mapping system, it causes many problems, but in that case, it still has problems. Problem has occurred when the price of the map update. So to reduce that cost, the crowdsourced mapping method I tried to use a number of vehicles. However, when the hardest part that how many users or normal users vehicles could be made as a vehicle, it can be a cheaper sensor than the normal MMS systems. So this is because the sensor to be installed also has an additional problem if the sensor does not already installed on the vehicle when they are sold by the finished car company, unlike Tesla. So it should be to be installed individually. Therefore, naturally, I believe that mounting the inexpensive cheap sensor on the large number of vehicles is the fundamental reason for solving the problems of the existing Heatmap creations and maintain method. Yeah, this is my answers.
Okay, thank you. Any other question? If there's no other question, I'd like to thank you, Professor An, for your participation. The next speaker is Professor Jiawei Han, Michael Aiken Chair Professor in the Department of Computer Science of the University of Illinois in Urbana-Champaign, United States. Paul, let's get with Professor Hans' talk.
Hi, my topic is on how to do text mining. Essentially, we propose an annotation-free pre-trained language model approach. Okay. So I'm going to discuss my topic in three aspects. First is we are facing very massive big data. However, 80% of big data actually is from the text, natural language, or social media. It contains major challenge is it is high dimensional, its semantics rich, but it's organized semantically in taxonomy. How can we use this this kind of characteristics? We propose to use weak or self-supervision approach. That means we think human substantial labeling or annotation cannot be scalable, but we do have massive unlabeled data widely available. We want to propose weak or self-supervision to solve this problem. So we propose to do embedding, structuring, and taxonomy-guided mining. I'm going to discuss a few interesting things we have been studying. One we call discriminant topic mining via category name guided embedding. If you look at the recent embedding approach people are discussing, so essentially doing WordFact, GlobalFast, or Jose, these kind of approach is doing, mapping the words with a similar context closer in the embedding space, but it does not impose any kind of a supervision or human guidance. Okay. However, if you look at the 6 examples here, you can see these 6 people, if we are discussing politics versus science versus literature, likely, like Theresa May and Donald Trump should be closer together because they were all politicians. Okay. However, if you are discussing England versus United States, you probably see Theresa May, William Shakespeare, and Isaac Newton should be embedded together because they are all from England. Okay. So can we get a method which can take care in the embedding space to respond some human guidance? Okay. So we basically consider it this way. If we have category on the documents, the category actually will have conditional probability on the documents. The documents may have conditional probability on the words, and the words may actually can intertwine with the surrounding other words. If we take all these probability into consideration in our computation, we should be work out some kind of a clustering method like EM algorithm, the things closer together. For example, food. You may find steak and seafood, salad and dessert may be surrounding the food. But if you look at the seafood, you may see crab, prawn, oyster, and fish could be closer surrounding seafood. With this idea, we actually developed a method called Kate. And this method, you can see, compared to many other methods, it has both topic coherence and mean accuracy, higher in many topics, like in massive New York Times on location guided embedding or topic guided embedding, or on Yelp on food guided and sentiment guided. You probably can see here. For example, if you look at New York Times on location, if you put 2 seats, Britain versus Canada, so the Kate actually give us much better meaningful results on Canada and Britain. And if you give other different topics, you will get a very different kind of topic words. The frequency is quite interesting and useful. Okay, we actually take this to analyze 2019 Hong Kong protest data. And if you just based on these protest data, you look at a political versus police versus economic or information infrastructure. What you need is just give a bunch of keywords as examples. And with this, we take these as the different categories. We conduct the embedding. The embedding will give us some much more useful, meaningful things in each category. Okay. Not only we can do it in the single level. If we want to do it in a hierarchical way, we can actually work out a method we call joint tree and text embedding. Essentially, is we can get the topic words in the top category and in the later lower categories. And by computing such embedding, you can get many more keywords or phrases related to each category and each subcategory. So that will make things much more interesting. And also we study how we can do classification, unstructured text classification. If you think about majority of the people doing classification considering only a small number of classes, like 10 classes or only 2 or 3 classes, but in reality, there could be, for example, in Microsoft Academic Graph, you may have 25,000 candidate classes, or even for product profilers, the category of this, it could be tens of thousands, okay? So the major challenge is we may have huge labor space and we may want a multi-labor tagging, but we have only very limited labor data. It's hard for supervision, okay? So, however, if you consider all the labor space actually arranged in the structure of taxonomy, like a tree or DAG structures, and with this, we should be able to develop a method to go step by step. For example, if we can get a document, we first judge within computer science what the children could likely, could be the parent class of this document. Then we can finally find the core classes. Okay. So how to find the core classes? If we go step by step from the top, go down, we actually can use pre-trained language model like a BERT or Roberta on the fine-tune on the natural language inference task. For example, if you get this document, and if we look at the whole structure, at the lower level, we actually can think about this paper is about NLP evaluation, but how do you know it's about NLP evaluation? What you can do is you actually can take, using natural language inference model, take this one as a premise, and as a hypothesis, you put a few candidates at that level, likely which candidate will give you the highest probability, okay? So you probably can see if we do this way, we can take like Amazon data like this as a review. Okay. Then you think Amazon, they start with product, they go down to the first level, then go down to the lower level. And thinking about it, you first try to identify which one likely will be the top class for the first level. And then you can go down to the second level, to the lower level, find the core classes, and trace back to see their parents or common grandparents. So likely we can get this multi-class classification problem solved without human annotation, but we only need a provided taxonomy structure. Okay. We actually take this into consideration, did this text class algorithm. You probably can see comparing with many other algorithms, this algorithm give you far better, like F1 value and precision at 1. Okay. And the text class actually could be hundreds of classes. Then another interesting one I would like to introduce is open vocabulary argument role prediction. That means if we take the open vocabulary, suppose we give you an earthquake like this. Can we go through automatically take a bunch of earthquake reports we'll find the most important arguments is magnitude, location, date, and time. And we also can automatically fill in the values. We have such an overflow with a framework called role predict. Okay, the role predict, the general philosophy is we start from the event type, like an earthquake. We extract a bunch of entities, and using this entity, we actually work out the templates and put into the pre-trained language model. We'll be able to grab the candidate roles, and with a candidate role, when we actually try to find the concrete structures and concrete values, we can use a question answering model. Using pre-trained question answering model, we will be able to derive the concrete data as well. Okay. So we can give you a simple example. Suppose you, at the very beginning in the earthquake, you only get this one, like 1964 Alaska earthquake, like this particular sentence. And from the sentence, we actually can add a prompt like this. After the sentence we add prompt is, according to this, the mass span of this earthquake is the concrete data, is the concrete value. With this, the pre-trained language model, like a generation model, T5, will give you this one will be like the time or start time as the argument role. That means from there, we should be able to derive the concrete argument role. And for person, location, number, and other types, what you need is just to slightly change the template, the prompt template a little to make it smoother, and it should work well. Okay. And then we discuss how to get our concrete argument value to be extracted. You can see if you have the new prompt like this, you put the document at the back, you put the question here. And the question could be, what is the casualty? That's the event role you already extracted. What's the casualty of this pandemic event? And from here, you can see, using BERT or Roberta, these BERT-based pre-trained QA model, you should be able to extract the argument based on this casualty, based on the concrete sentence. You will be able to extract the argument. The casualty should be 5 million. Of course, sometimes you try this prompt, you may not get a high quality one. You can think this question for this particular sentence is not answerable. Okay. And with this, we actually can work out how to get rows and how to get arguments. Okay. With the rows, we actually can see is if you have multiple events for the same type, like earthquake, you probably will find that the multiple events, they all share the common role, for example, intensity, and that intensity likely will be important one. And for a war ceremony, you find the host could be important one. That means a role name may belong to the event type only if most of the event instances have their associated argument. So you base on popularity vote, you will be able to find the most important roles. However, sometimes the roles using the pre-trained language model can give you some different ones, like date, official date, and original date. So for the event like fireworks. And with this, which one is correct? Okay, or they can be merged. So we basically say if you have multiple instances of firework event, then if you find the two rows, the date and official date, have the same day as the argument in multiple instances, their similarity is high, they can be merged. You can see, using this, we actually took the earthquake, okay, and took many other rules. For example, this event type is shooting. we take the shooting, we actually can find a lot of very interesting ones, and some different role names can be clustered and merged. And with this, you can see our method can find many more roles than many state-of-the-art methods. Okay. So our general philosophy is we try to promote weakly supervised mining of massive data. That means if we want to handle text mining, our important framework is we start from large text corpus and a general knowledge base like Wikipedia. Then we can use pre-trained language model, can use data mining approach, find phrases, find fine-grained entities, and construct multifaceted taxonomies and a multi-dimensional classification cubes and multi-dimensional knowledge graph or information networks. Using these structured data, we should be able to systematically mine the knowledge out of text. Okay. So that's basically our general philosophy. Hopefully you think this philosophy will be very promising in the future studies. Thank you. Yes. Thanks for listening. So I'm here, so I can definitely handle a lot of questions if you're interested.
Any questions? Well, Professor Han, thank you for a great talk on a very difficult but very important subject. There are a few questions for you.
Yes.
Your enhanced text embedding methods have shown very good results against benchmark data. But have they been applied to some real applications? If so, what are the actual results and practical benefits that you have seen?
Yeah, so we have done a lot of collaborations with many people. For example, a few years ago, 2 years ago, like I showed the Hong Kong protest, the analysis. At the same time, actually, Army Research Lab, that time they collaborated with us. They asked us to analyze like a Russia-Ukraine conflict. That time was a smaller conflict. They actually mainly is in the Donetsk, that area. So we analyze, we give them, all the different categories. They ask us, for example, we give like, they give one called politics, one called military. We actually categorize like a pro-Russian as politics, but pro-Russian separatists as military. They say it's interesting because if you look at the pro-Russian definition of political view, but the pro-Russian separatists were those people who really served almost like a paramilitary fighting with the government army, so that they count as military province or property. You can see there's no supervision. What they need is just give us a few categories. We extract from the corpus lots of different kinds of data. Actually, this year, with the Russian, invaded Ukraine, we actually just use the same algorithm. We show, for example, if you give a Kyiv, you give a Bucha, you give Mariupol. Actually, we give all the different phrases surrounding to each city what's happening. It's very telling. Everybody, they look at it, like in Bucha, they look at all the massacre, how the people died, all these things, all these phrases crowded in Bucha. So you clearly see you don't need human, it's just a machine can automatically grab it. Actually, IBM this year, there's one team worked with us. They found this one. They say, can you actually grab from the software engineering bug analysis data? You can say this one's a software bug, this one's operating system, this is a database phrases or something. We use exactly the same thing. We just go inside and grab all these. They actually think it's very telling because Some are about the software category errors. Some about like a booting or starting. Some is about operating system or different versions. It's almost like human experts, but there's no training. And what you need is just putting those key phrases down there, and you can get it. Yeah. Thank you.
Okay. I have another question.
Yes.
The taxonomy-based weakly supervised classification is very interesting and promising. But in your opinion, what are some of the limitations that you would like to overcome? For example, it's not clear if a clear-cut hierarchy is usually possible, since one document may semantically belong to multiple classes. Further, it seems that given two classes, class 1 may be the parent and class 2 the child, or vice versa, depending on one's perspective or purpose.
Yes. Yeah, that's a very good question. The first thing is we actually assume people do give you a taxonomy. The taxonomy can be a DAG structure. That's exactly Microsoft research. They give us a Microsoft academic graph, which is very big. But actually, some people, some node may have multiple parents. For example, you even look at the GPU. One parent could be in the hardware, the other one could be in deep learning. So that's quite appropriate because in different analysis, you do get this. Another thing is we actually do multi-class classification. That means we are not only give you one label. This is more like a document. In many cases, when the author want to write, they give you a choice, writing a bunch of keywords instead of just one. We actually, even you look at that children's baby cereal, you actually can see one part goes to gourmet, the food. One part goes to baby because it belongs to both. Actually, what we are getting is a multi-class classification. That means we actually find even more than one core class. And then we go down, normally their parents or common great-grandparents could be very good candidates as taxonomy. So this multi-class classification is very useful because in many cases, you don't want to miss those things, okay? So I think in practice, it's very useful because if you have hundreds of classes, you may want to label these documents in different categories, putting the most important one as a core class, and their parents or grandparents could also be useful. Yeah, thank you. Hopefully this answers the question.
Okay, thank you.
Thank you.
If there's no other question, will Professor Ong-Lan Chung say hello to your mentor, Professor Jiawei Han?
Yeah.
You have an opportunity here.
Yes. Yeah, I saw lots of names. I know lots of friends are online as well. Thank you. Like Professor Lin Tak Wang, we know each other for like 30 years. We're all friends.
Yeah. In fact, I have one simple question. Okay. You see, when you talk about some article or something, okay, in social media, sometimes certain thing, the object, if you say John, okay, I know who is John, but the thing, John in general cannot be identified because it's not unique. But the thing in the context of the social people, the context, okay, they all know who is John. That means it's context sensitive. Or an article mentioned about London. In Canada, Canada has a city called London. But the thing, London in UK also has London. So the article appear in Canada called London. It's different from the article appear in UK called London. There's a context.
Yes. Yeah, that's a very good question. That's exactly, we are promoting this pre-trained language model because the pre-trained language model does take care of the context. It's very important. And you probably can see in many cases, the same word, same phrases in different contexts may mean different things.
Yeah.
We typically use, for example, like a bank or Apple. In different contexts, it really different things. Yeah, I think that's exactly the power of pre-trained language model.
Okay.
Because with this, it's much easier to identify things based on the surrounding context. It's very good, a very good point.
How about the order of the two words? Because the order, if they are different, may completely different meaning.
Yes, that's very true. That's also why the pre-trained language model embedding will be so useful, because typically in the past, the people are actually using they call vector space model. Vector space model treat the documents as a bag of words, which actually is not accurate at all, because you don't really have the context. That's why with deep learning, people actually crowded now down into the pre-trained language model, because this one does take care of context. So you would see in the whole natural language processing text mining field, once this pre-trained language model comes, everybody now is using deep learning pre-trained language model to do things because it catches the context much better. It promotes the natural language understanding in a much more powerful way.
Yeah, thanks a lot.
Yeah.
Okay,
thanks.
Let's move on. Thank you again for your participation, Professor Han. Please say hello to your wife, Dora, for me, and I hope to see both of you soon somewhere.
Yes, thanks a lot, Professor Kim.
Have a great day.
Yeah, you too. Bye.
The final speaker is Professor Sharad Mehrotra, Chancellor's Professor of Computer Science with the University of California, Irvine, United States.
Hi, I'm going to talk today about DB, a data management system we're building at UCI for smart space applications. I'm Sharad Mehrotra. I'm a professor of computer science at UC Irvine. So smart spaces, according to Gartner, is technology which is basically going to be embedded into physical environments that can interact with humans. And it is expected to be among in the 3 to 6 year horizon, one of the 5 most dominant technologies that are going to be around. The smart spaces are going to influence almost every aspect of our lives, whether it be smart campuses, smart buildings, communities, hospitals, transportations, offices, malls, whatever. All our living spaces, they are going to be able to interact with basically humans, and through sensor technologies, by observing humans in the process of interaction with the spaces and with each other. So if you think of data management challenges for smart spaces, we obviously have the 4 big V challenges for big data, which is volume, velocity, veracity, and variability. But in addition, the things that sort of we are addressing in our work in DB for building a database technology for smart spaces are the next 3 Vs. One of them is pervasiveness. So by pervasiveness, I mean cost-effective, ubiquitous sensing of people and activities. So a critical component of being able to build smart spaces is the ability to locate people and the interactions with each other and with space, which requires us to essentially localize people internally inside the buildings as well, not just on the outside building through GPS, but inside buildings as well. Indoor localization, while it's been deeply studied, is still an open problem, and a cost-effective solution of that has evaded us so far. Another big challenge is privacy. So whenever we observe people and the interactions in spaces through continuous monitoring, there is a natural challenge of leakage of personal information, which has to be addressed. And this privacy challenge, while there is a significant body of work in privacy enhancing technologies over the last few years, such solutions do not address essentially the privacy challenges in dynamic sensor environments. And finally, there's a challenge of data virtualization, by which I mean the semantic gap. So data in sensor-enabled spaces arrives in the form of sensor data, which is often too low level to be used for applications itself. Existing databases do not support the right level of abstractions to translate the sensor data into higher level observations. And any logic which requires, let's say, this higher level translation has to be done then internally by application logic itself, including logic for, let's say, dealing with heterogeneity of different sensors, for tolerating failures of sensors. So one sensor fails and then there's a failover to another sensor. So all that logic has to be now embedded inside the application logic itself. In TPSDB, our goal is to develop a middleware solution which sits on top of a database system, serving largely as a storage engine. And the goal is to support basically scalable execution of sensor-driven smart space applications while building in the concept of privacy by design. There are three main components to TPSDB. The first is the locator technology, which is intended to support pervasiveness. And the idea here is to sort of exploit existing Wi-Fi infrastructure, which is ubiquitous. So when people connect with Wi-Fi, let's say networks or Wi-Fi access points through their cell phones or through their mobile devices, we can use that for localization. Now, exploiting Wi-Fi technology for localization is not a new idea. It has been ongoing for a certain while, so a significant amount of time. But what Locator provides is a bunch of data cleaning technologies which exploits the semantics and exploits, let's say, interactions between people and spaces to achieve very high level of accuracy, both at the coarse level and the fine level of fine granularity of localization. So including about 90% accuracy for room level localization. And with this level of optimization, it competes with the commercial solutions which are hardware-based or expensive hardware-based solution that requires new hardware to be brought into environments. And therefore, it enables applications to be built while addressing the zero-cost challenge of the pervasiveness. The next technology is PIOT. This is essentially middleware technology for privacy. The idea here is that whenever data flows into the system, into TPSDB, or goes out of TPSDB to applications, it is basically subject to interference, or it's subject to being basically injected with privacy technologies. So these technologies could include policy maintenance or different policy-based approaches, as well as differential privacy and any other mechanics, cryptography and so on. So for instance, the policy can be specified that when data goes from, let's say, the sensor stream into a disk, the policy might be that the data at rest has to be encrypted. So in this case, the system will automatically encrypt the data. So PIOT essentially intercepts the flow of data and injects the privacy technologies inside it. And finally, there is a TPSDB core engine, which is the goal of which is to build a database technology with data virtualization built in, and it supports lazy progressive computation. Today, I'm going to focus primarily on the TPSDB core engine and not on Locator or PIOT. So let's start with a given example of virtualization. So virtualization, as I mentioned, data virtualization refers to ability of a system to dynamically interpret the semantic interpretation of data based on sensor data prior to the data being used in the application. So let's take an example. So sensor data, for example, could be a camera data which comes in. Now this camera data could be from an in situ sensor, a camera, or it could be from a hand-carried camera. The interpretation of the data, which is down below, could potentially be that a semantic observation of this data could be that John, a person named John, is in room 4206. Now, to be able to interpret from this camera data to the fact that John is in 4206 requires translation. And this translation logic could actually be pretty complex. First, to interpret that this is John, we may have to face recognition, or even do semantic reasoning of the following kind, that the room that's, let's say we knew the room that's being entered to is 4206, in which case we could sort of figure out that this room belongs to John and therefore the person entering in could potentially be John. Likewise, for location determination, we may have to significant amount of spatial reasoning as well, and based on maps and other information that in case of, let's say, in situ sensor, this may be a bit easier, because given a sensor, I may know that this particular sensor or this camera will be able to observe room 4206. But what if this was a mobile camera carried by somebody else? In this case, location of the mobile camera has to be coupled with the information about the doors and which rooms are at rear to sort of interpret that this is room 4206. Finally, both of these coming together will give us a fact that John is in room 4206, which can then be used to build applications on top. There are several advantages if a system automatically supports, or at least supports, data virtualization. First, it will make your programming task for application developers much easier. So application developers can focus on the application logic instead of having to deal with sensor data and basically reason about sensor data in the application code. It offers us this degree of separation between the sensors and the application logic or application or semantic knowledge. And it offers a sensor and functional independence very much like the data independence offered by databases. There are several additional advantages that are sort of implied already in this separation of concern or sensor and data independence. First, we have an ability at this stage to dynamically add new sensors. So imagine an application is built and at a given instance of time, there were only a few sensors that were installed into a building, and later more sensors could be added. Now the application logic doesn't have to change because the application logic does not deal with sensors, but with higher level observations. The new sensor added will provide us the ability to interpret possibly better the same semantic observation using the new sensors. Likewise, the flip side of it is fault tolerance. So imagine if there are several possible sensors that could be used to observe the same phenomena. If one sensor fails, the system automatically will shift to the next sensor so that there's continuity in the application, the observations remain available to the application. And then there are applications of scalability and optimization opportunity, very much like when we write basically SQL programs at the higher level of abstraction, the translation of the programs to potentially an optimal plan, query plan, and execution plan. A similar kind of a concept is applicable here as well, where the system can help us in optimizing the execution of the query as well. The benefits of virtualization does come with certain amount of new design choices and certain complexities. First, there is a complexity of, in this case, that enrichment that has to be done on the data cannot necessarily be done at the ingestion time itself. So let's take an example from UCI campus that we have built. So at UCI, there are about 40 million location events that arrive every day from basically interactions of people carrying devices with access points. These are Wi-Fi events that occur. Typically, at the course level of granularity, if you want to use this information to interpret, let's say, the region in which a person is, we can process about per second of data requires 14 seconds of processing. If we want to get fine-grained localization to room-level location of a person, the same 1 second of data requires about 300 seconds of processing. Clearly, this cannot be done at the time of basically ingestion of the data itself, requiring an adaptive enrichment strategy where we may end up doing some part of the enrichment at the ingestion time, some part of it at different events time, and obviously some part of being done at the query time. The advantage of doing this in processing at query time is that we can only enrich the data that we require to answer queries. We don't have to enrich the entire data set as well, therefore providing great savings. But if we were to do the enrichment at the query time, we have to think in terms of what is the implication of that to query languages, to data model, to support enrichment. Furthermore, we have to also address the issue that since enrichment is happening at the query time, it can increase the latency of query because now you're running expensive ML code inside the query execution itself. To address virtualization or to build data virtualization, TPSDB supports a data model, which basically has data represented at sensor layer. This is basically where all the data comes in, the data flows into the system of different kinds and gets stored. Then there's a semantic level. So application writers will model data at the semantic level where there are semantic concepts such as rooms, occupants, residents, visitors, and all of the concepts that one has in a typical application setting. The fundamental difference between this, the model that the TPSDB supports versus the regular relational model or ER models that we're used to, is that we have this concept of dynamic properties. So associated with concepts or with entities such as room may be a concept of occupancy, which is an attribute that's dynamic. Dynamic attribute means that's interpreted direct from sensor data during execution time. Likewise, relationships could also be dynamic too. So an occupant, for example, is located in a room based on a sensor. We can make the observation, and when the person goes out of the room from the sensor, we can observe that he has left the room. So relationships between things can arise from the sensors as basically the environment through the flow of data from sensors. Then there is this concept of translation. So in the data model, there's a translation layer, which consists of observing functions where you take this lower level sensor data and you map that into corresponding concepts as location, occupancy, energy utilization, vitals, contacts, and all that stuff. So let's look a little bit more into query-driven translation. A user ends up writing applications at a higher level abstraction. So here is an example of a query which is saying, find me all rooms where John visited during this interval of time, having occupancy more than 50. Notice that occupancy is basically a derived attribute, or it's a dynamic attribute. Therefore, to be able to determine if occupancy is more than 50 will require some sensor processing. Likewise, John's location is not known in advance, and that again will require sensor processing as well. So what TipplesDB will do is it'll take query of this kind, it'll translate into a query tree, and it'll then do analysis to figure out which attributes are dynamic attributes, and based on that, it'll place translation operators before the predicates of those attributes are evaluated. So in this case, before location, to determine John's location, we have to sort of do the translation of the location attribute, and likewise for the occupancy, for the occupancy translation has to be done for the translation of the occupancy as well. These translations are actually a fairly complex piece of logic. What it has to go through is, given the operators, it has to first go and figure out what kind of sensors can be used for this translation, then just choose appropriate sensors to determine if the sensors are available or not. Then, given multitude of sensors that could potentially give us the location of a person, it has to come up with all the different choices and figure out, based on a cost-benefit analysis, the right set of sensors to use to do this translation. And then finally, the translation will execute based on the functions that have been chosen. Complexities arise because the translation itself is expensive. It requires, as I said, ML functions to execute in the middle of the execution of this translation. Furthermore, depending on the kind of sensors available, this aspect of multiple sensors may actually be able to feed or use to basically determine a specific semantic attribute. It can lead to an exponential number of possible plans. And this, therefore, the system has to then choose from those exponential number of plans the right plan to execute a particular translation. Given the expensive nature of translation, there are several optimization TipplesDB tries. I'll give you an example of a couple of them. So one of the things that we use is hierarchical filters. So for example, here's a query, again, same query where you're doing translation of room and translation occupancy. What TipplesDB realizes is that in case of translation of a room, for instance, to be able to get location at room level of a person, it's much cheaper to first get a region level location. So there's a hierarchical representation, containment hierarchy, which is sort of inherent in the fields such as location, and that's true for almost every field, not just location field, but I'm illustrating it for location field. So there is this hierarchical representation, and it is quite possible that it's cheaper to execute the translation at the region level compared to the room level. So TipplesDB will automatically incorporate such a translation or such a filter into this query tree, and it will first do the region level filtering, and only the things that meet the region level filters will then go to room level filters. Another optimization we do is contextual filters. So for example, just continuing with the example of John, so if our goal was to find location of John at a given time interval, this could be a really hard query because effectively John could be anywhere in the campus and there are thousands of sensors to go, or even tens of thousands of sensors to go to sort of figure out the location of John. Instead of going through tens of thousands of these different sensors, if imagine there's a contextual information available, which is in the form of, let's say, last known location of John. So if I know where John was, let's say half an hour ago, I can exploit that information to cull out or at least prioritize which particular sensors to execute when, so that we can reduce the cost of translation to be able to determine where John is. So this is contextual filters, which can be very effective in reducing the translation costs of queries or of semantic phenomena. Now that we have translation functions and given a query tree, one way to execute the query would be to sort of blockify them and chop them into blocks across translation boundaries. Remember, the translation has to be done basically in the middleware, so we can take this piece of code and sort of execute the subqueries prior to the translation, and then materialize those queries, give a result to then do the translation and continue the query processing. If we do something of this kind, obviously there's going to be a significant overhead in terms of an inefficiency, because prior to the results percolating to the top, we'll have to execute a large amount of execution or wait for the results of all the different blocks to come through before the results can be shared with the user. So instead of that, TripleDB implements a progressive query execution. And the way it works is that instead of executing in a block-oriented way, TripleDB takes time and divides it into epochs. And in each epoch, certain set of entities will be chosen and they'll be translated. Based on these translated entities, we will then be able to answer a query results approximately. And then as in the next epoch, additional things will be translated, and then the query answers will be improved. So here's the illustration of how TripleDB executes such queries. I may, if my goal was to find, for instance, where John is in a given day, I may do localization at the floor level. As time goes on, in the next epoch, I may then refine the answers to do the localization at the region level, and then it'll go finally to the room level localization as well. To be able to do progressive execution, we have to do the implementation details can be complicated, but effectively what we do first is identify an approve query, which identifies for each semantic concept to be determined what is the set of minimal set of entities that we have to translate to be able to correctly answer the query. So once we have this basically probe queries identified, we exploit incremental view maintenance technology to set up the query execution and also the execution of the probe queries using the IBM technologies to most effectively execute the query in a progressive fashion. So the details again are complicated and I will not have time to sort of go into it, but you can look at the website and also the papers associated with the system. So we set up the evaluation, and again, in the interest of time, I'm going to skip a little bit of the details here and go straight to illustrating you a example of progressiveness. So the green line here shows effectively for a query which was actually quite expensive, would have taken in the order of, let's say, hours to execute without basically appropriate progressiveness and without optimizations, is able to execute in a fairly quickly way in a matter of, let's say, a few seconds to minutes, and give you pretty high quality answers. TripleDB has been built, and it's still under development, but portions of it have been built, and it has been deployed in several places. It has been deployed at UCI. It has been used with a variety of different sensors, and it's been deployed in about 30 buildings in our campus. It's used for a variety of applications such as localization, occupancy levels, flow control. One of the main uses of this was during COVID times when we were using the system to determine, let's say, how many people flow through different parts of different buildings, what are the occupancy levels of different buildings, and so on. It's also been adopted by other schools and campuses, some of which I've listed below. It was been also transitioned to the Navy, where we participated in a Trident Warrior exercise, where it was a winner of a Never Innovations Award. And most recently, we've installed this in Walnut Village, which is a senior living facility, to help with emergency evacuations. In conclusion, TripleDB is a database technology for smart spaces that implements privacy by design, supports data virtualization. It supports and has tools for rapid deployment. It has also built-in mechanism for indoor localization, and it is sensor agnostic. I would like to thank a bunch of students. This has been the work of a lot of different people. Some of them are shown in the picture right here. And if you're interested to find out more, you can go to the website, which is tippersweb.ics.uci.edu. I intended to show a video of the system working, but I don't think I have time for that. But you can go and the video is available also at this website, so you can have a look at that. Again, the website is tippersweb.ics.uci.edu. Thank you.
I'm sorry that due to the time difference, Professor Mehrotra cannot be present for a real-time Q&A. If there's any question or a request, please send it to me and I will forward it to him. This will conclude the second annual forum on ABC. I would like to thank the speakers for preparing the talks and being present for the Q&A. I also would like to thank all the participants for their time and interest. I owe special thanks to the participants in Korea as the World Cup football game between Korea and Ghana is being played. Thank you all. Good night, good afternoon, and good morning.